Hey, my name is Jay. I'm an instructor at Kaitoki Outdoor Ed Centre, and part of the mission for Y Outdoors at the moment is creating some online content for you guys, for anyone who's interested in continuing learning at home. I'm going to create a couple of tutorials on something that I find pretty interesting at the moment, and that is weather. Not only do I find it pretty interesting, I also think it plays a pretty big part in an outdoor instructor's life in terms of keeping people safe, so predicting the weather and looking at the weather and knowing what's coming up. But it also plays a part in just anyone's life, really, if you are doing things in the outdoors and you want to make good decisions around safety. This is the first one, and today I'm going to be explaining how dew is formed and why. So at the end of this, if you watch the whole thing, you will be able to explain and know why dew forms. And the reason that this is a really good place to start is because to understand how and why dew forms, you need to understand a lot of underlying rules about our atmosphere, which also play a massive part in basically all weather. But it's a cool place to start anyway, being able to understand that question. So here we go. The first thing we're going to have a look at, we're going to have a look at a whole bunch of different things that kind of don't make sense and how they fit together at the start, but at the end you'll see. And the first thing we're going to have a look at is the heating and cooling of Earth in general on a big scale and why that happens. So you might already know this, and that's great, but I'm going to go over it anyway. So this is the Earth. It's a circle, just goes off the board. And we all know that the sun, which is over here, is what is heating up the Earth. We all know that in the middle of the Earth is this invisible line, which is the equator, and at the top and the bottom we have the North Pole and the South Pole. We also know that the equator is warmer than the poles, and that is because of the concentration of solar energy emitted from the sun. Common misconception is that the equator is closer to the sun than the poles, and that's why it is a different temperature. That's not the case, and I will explain what concentration of energy means just in case we don't know. So the sun emits energy, and this energy coming from the sun is called, I hope you can read that, solar radiation. So solar radiation from the sun is coming to the Earth. Now I'm going to draw this as kind of like a beam of solar radiation, like this. So we have a beam of solar radiation coming from the sun and hitting into the Earth, and we can see from this that the distance, so it's heating up the surface of the Earth, the distance in which it's heating up is about that big. If we now draw the same amount of solar radiation, so the same distance coming from the sun, but going to, I'm going to rub up my own line, to the equator, same distance. Awesome. Kind of doesn't look like the same distance, but it is. We can see that the distance, or the surface area that it is heating up, is greater at the poles than it is at the equator. So the more concentrated that same amount of energy is, the hotter it's going to be than at the poles where that energy is spread out a lot more. You can do this demo real quick at home. If you have a big ball and a torch, you can stand a certain distance away from the ball, you can shine the torch on the ball in the middle, and you'll see that the distance in which the light lights up is smaller. If you just stay in the same place but move the torch up to the top, it'll be a greater area. It's the same amount of light coming out of that torch, it's just heating up a different area. Cool. Well, we can rub out quite a lot of this now because we get how that works. Awesome. So solar radiation from the sun is coming in and it's heating up. It's doing a whole bunch of stuff, but in terms of heating, it's heating up the surface of our Earth. Now, the surface of our Earth is also taking that heat and it's emitting it, and so energy is coming out as well. Energy coming in, energy coming out. And the energy coming out is called terrestrial radiation. Solar radiation coming in, terrestrial radiation coming out. This terrestrial radiation, so the solar energy that's coming in is heating up the surface of the Earth, and the surface of the Earth is therefore heating up the air that is in contact with it. So we know that there's air around the Earth. It's what we're breathing in right now, or what you're breathing in right now. And that air is being heated up by the surface of the Earth. It's being heated up by contacting the surface of the Earth, which is being heated up by the sun. The balance between these two energies, so there's energy coming in and energy coming out, is called the energy balance. Why is this all important? Or to recap, so energy comes in from the sun. It's more concentrated at the equator than it is at the poles, so it's heating up the equator or the equatorial regions more than it is heating up the poles. This energy, in terms of warming, heats up the surface of the Earth, which then heats up the air that is in contact with it. So what we can take away from this is that the air around us is being heated from below. It's being heated by being in contact with the surface, which is being heated by solar radiation. This balance of incoming and outgoing energy is called the energy balance. Awesome. So, we know that we have Earth as a planet, and this planet is surrounded by an atmosphere. So we're going to have a quick look at how that's made up, because it plays a massive point in weather, huge point in weather, and also the answer to our question that we're going to come to at the end. So our atmosphere is made up of a whole bunch of different gases that you right now are breathing in, and we'll go over some of them now. So the first one is nitrogen. The second main one, is oxygen. Then we have argon, and I'll just draw it up here because I've run out of room, other. So these boxes aren't perfect, but essentially they represent the amounts of each of these. So nitrogen, there is 78%. That's a rough percentage, it's a rounded percentage, it's not quite that, but just for the purpose of this, it's about 78. Oxygen, 21%, argon, about 0.9, and other, about 0.1. And all of these add up to, of course, 100%. Pretty basic. Again, this other, there's a whole bunch of gases in here, like CO2 and other things that make up other gases. And if you were to go online and to Google atmospheric makeup, you would find something like this. It might be a pie chart, or it would just explain all the different percentages. What you would never find, however, is the percentage of another gas that is always in the atmosphere. It's in the atmosphere that you are in right now, that you are currently breathing in. And the thing, or the gas, that is always in the atmosphere but not depicted in any of these atmospheric makeup charts is water, or water vapor. Water vapor is in our atmosphere all the time, and it's never depicted in these charts because water vapor is what is called a variable gas, which means there is a different amount of it in the atmosphere at any one time. You can't have something like oxygen, which is fairly consistent. Water vapor varies depending on where you are, depending on the type of day, season, all sorts of different things. So it's never in this makeup. From that, we can then assume that this atmospheric makeup is what we call a dry atmosphere. So it's an atmospheric makeup with no water vapor in it. However, water vapor is in our atmosphere, it's in your atmosphere, and it will be around you right now, although you might not be able to see it. Or you. So, what does that look like? Well, I'm going to start off with having a look at some measurements of how we measure the amount of water vapor in our atmosphere. And we're going to start off with a box. And this box has, it's 1 centimeter by 1 centimeter by 1 centimeter size. So this then you could say is 1 centimeter cubed, 1 cubic centimeter, pretty obvious. If you were to take this cube and you were to fill it with water, you would have exactly terrible writing, you would have 1 gram of water. Now, I'm quite a visual learner, and for any of you at home that are also visual learners, this size here is about the size of a die that you'd use for a board game, just so that you can get this against something else I'm about to draw. So about the size of a die. If you hollowed out a die and filled it with water, you'd have about 1 gram of water. I'm going to draw a bigger box up here. And this is a box that has 1 meter by 1 meter by 1 meter. So it's a much bigger box for anyone who is a visual learner. Again, about a meter is usually about the distance between the floor in your house and the door handle on any door. So if you just think about that as a big cube, you can see the difference between these two boxes. If we were to fill this box up with water, we would have exactly 1 kilogram of water. Now, we're going to have a look at the difference, or a different way of measuring water vapor in air now. So we're going to fill up this box with air, and we're going to fill it up with dry air. So the stats that we looked at before, no water vapor is in there, it's just 100% dry air. And luckily for us, there is a door on the side of this box, and we are going to open that door, and we are going to put in 3, let's just say they're ice cubes for this demo, 3 ice cubes exactly 1 centimeter by 1 centimeter by 1 centimeter, which means about a gram. We're going to pop them through the door, and obviously they would sink to the bottom, so we would now have 1 kg of air and 3 ice cubes sitting at the bottom. If we left this long enough, we would find that these ice cubes would melt. So we now have 3 puddles of water sitting at the bottom, and if we left it even longer, we would find that these puddles of water would evaporate. So it's water just changing state from ice all the way to water vapor. So the puddles would be gone, they would have evaporated, and it would kind of look like there was no more water in the box, because you can't actually see the evaporated water. It's now part of the air inside that box. So what we would have, what we've actually just made, is a measurement. So I'll take that away, we know that now, is a measurement of 3 grams, because we added in 3 ice cubes, so we added in 3 grams of water per kilogram of air. That is the measurement that we are looking for. So this measurement here is called the mixing ratio. And that mixing ratio is one way of measuring the amount of water content in a mass of air. So, real quick, we could also now add in 3 more ice cubes, so 3 more grams of water. They would do exactly the same thing. So they would fall to the bottom as ice, they would then melt into water, liquid, and then eventually they would evaporate into this 1 kg of air. And we would no longer have 3 grams per kg. You would now have 6, because we've just doubled it. So we're actually just creating this mixture based on the water content of that air. And that's kind of how that works. That's how that looks. There are two really, really important things that we need to understand about this before we move on, this mixing ratio. So the first thing we need to understand is that if I took a cup and I scooped out some of that air and put my hand or put a lid on it so that nothing can get in or out, the mixing ratio inside the cup is exactly the same. Although we don't have a kg of air anymore, we have a smaller amount of air, we also have a smaller amount of water vapor. Not all 6 grams goes into the cup, so the mixing ratio is the same. It doesn't matter the size of the air mass, the important thing is the mixing ratio. That's what counts. The other really important thing we need to know is this. If we open the door again and we add in 3 more ice cubes and shut the door, they again would melt and evaporate, and we added in 3 more, and so on and so forth. Eventually, it would get to a point where you'd add in ice cubes and they would melt into liquid, but they would no longer evaporate. They would just stay as water on the bottom of this square. And that is because air has a maximum amount of water vapor that it can possibly hold. So you can keep adding in water and eventually it would no longer evaporate, which means the air would be full of water, could not add any more. And when this happens, it's called something. I'll just move this, 1 kg. The air, when it is absolutely full of water, is called saturation. Or we could say it's saturated. So air that has a maximum amount of water content in it, can no longer take any more, is said to be saturated, or it has reached saturation. Okay. The point in which air reaches saturation is different for different air masses, and it depends on the temperature of the air. So, really, really basic. If you have warm air, so air that's really, really hot, it can hold much more water content than colder air. Colder air can hold less water content. And what I'm going to do is, I've actually printed off a table that I'll chuck on this side now. Awesome. So, I'll explain this. On this side of the table, so the side closest to me, we have a bunch of numbers, and these numbers represent air temperature. So temp up the top, 0, 5, 10, 15, blah, 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 and then 10, minus 10, minus 20, minus 30, minus 40. So getting colder, getting warmer. On the other side, the side furthest away from me, we have the amount, so that this is the total amount of water vapor that air at this temperature, or any of these temperatures, can hold. So grams per kg. Couple of easy things to notice from this. So the warmer the air, the hotter the air, the more water content it can hold as a maximum. It doesn't necessarily mean that 30-degree air always has 27.2 grams per kg of water content. It just means that that is the maximum amount it can hold. It can have 0 up to 27.2, anywhere in that gap, but it cannot hold more than 27.2. And we can see that really cold air, like minus 30-degree air, can have only a maximum of 0.3 grams per kg. So a tiny amount compared to like a plus degree. So that's the first thing. Hotter air can hold more water than colder air. And the second thing that we can see from here is that cold air is always dry. It's always dry. Minus 40 can hold a maximum of 0.1 gram per kg, which is very, very small amount. Whereas warm air can hold a lot of water vapor content, or it can hold none. So the gap is huge, whereas cold air is always dry air. So I'm going to draw another box. Awesome. And let's just say inside this box we have 7.6 grams. This is a kg. Oops. So we have a box just like before, and inside this box is 1 kg of air, and inside this air we have a mixing ratio of 7.6 grams per kg. So I'll just write that over here, 7.6 grams per kg. Awesome. Let's just say for this demo that the air inside this box is 25 degrees. 25 degrees C. The question is, can the air inside this box, if I put ice cubes through the door inside, would they evaporate eventually? Would they turn into liquid and evaporate? And we can see that at 25 degrees, the maximum amount of water content that air can hold is 20.1, and the air inside this box only has 7.6 grams. So the answer is yes, this air here can hold more water content or more water vapor, and therefore those ice cubes would evaporate. We're going to keep going. We're actually going to cool this air down now. So we're going to cool it down from 25 to 20 degrees. And same question, pretty simple. 20 degree air can hold 14.7 grams per kg, and this only has 7.6, so it can hold more, which means water would evaporate. We are going to cool it down again, so we're going to cool it down to 15 degrees. Same question, 15 degrees, 10.6. 10.6 is higher than 7.6, so there is more room for more water content, which means it would evaporate. So we're going to cool it down even further to 10 degrees. So now we're at 10 degrees. We can see that at 10 degrees, the maximum amount of water content is 7.6, which is the same amount of water content that is in this box, which means that this air at 10 degrees is now saturated. So the air is holding the maximum amount of water content that it possibly cannot hold any more. So I'll just do this. Lovely. This air is now saturated. Maximum amount of water content. But what happens now if we cool this down even further? So we are now cooling it down to 5 degrees C. We will see on this table that 5 degrees or 5 degree air can only hold 5.4 grams per kg of water content, and we have 7.6. So there's a couple of grams of water vapor that the 5 degree air cannot hold. So that doesn't work, as we know. So some of the water inside of that air has to come out. And what it does is it comes out of the air and it sticks to the side of this box. Little droplets. So this process, when water comes from its gas state into a liquid state, is called condensation. Put it up here. I'm sure we've all seen condensation before. So that the 5 degree can only hold 5.4. There's 7.6. Some of it has to come out, and what does it do? It comes out of there and it sticks to the side of the box. It's not raining, it's just sticking to the side as small little droplets. Awesome. So this now is basically coming to the end, and we're just going to put everything together, and we should be able to answer the question that was posed at the start of this video. So we have a sun that is heating up the surface of the Earth. The surface of the Earth then heats up the air around us, and at night the sun is no longer shining on the part of the Earth that is at night, which means that the solar radiation coming from the sun is no more, but there is still terrestrial radiation leaving the Earth, which means that the Earth and the air around it therefore is getting colder at night. At night, sometimes, doesn't happen all the time, but sometimes the terrestrial radiation can escape enough that the air temperature cools down below the point that the air is saturated. So it gets to a point where the air is saturated, so it's holding the same amount of water content than it can possibly hold, and if it cools below that, some of that water content has to come out because it can't hold anymore, and it comes out as little water droplets, which is not rain, it sticks to things. And this is the phenomenon of dew that we see on a very cold morning when the air is cooled down below a certain point, and some of that water content inside that air needs to come out, and what it does is it sticks to the ground. And a lot of the time you'll find that it sticks to grass, and that is because grass is really thin and it cools off first. Thin things cool faster, so it'll stick to grass before it will stick to other stuff, but sometimes it can cool enough that it just sticks to everything. And that there is the reason why we have dew all over the ground on a really, really cold morning. Yeah, thanks for watching, guys. If you have any questions about any of this, or I didn't explain it well enough, then you can comment, and I'll answer any questions that you have about this in the next video. Cheers!